All right, so today's video is looking at Module 1, Topic 1, Lesson 2 for Algebra 2, which is generating algebraic expressions. And this is in your book on page 13. So in the last lesson, we looked at some patterns. Now we're going to take those patterns and really put the algebra into those patterns and identify equations and formulas based off of those patterns. So our learning goals are generate algebraic expressions using geometric patterns, represent algebraic expressions in different forms, determine whether expressions are equivalent, and identify patterns as linear, exponential, or quadratic using a visual model, table of values, or a graph. Okay, so let's go ahead and start with the three review problems, which are we're evaluating expressions that have a power, specifically a squared. So I want you to pause the video and I want to see what you can do with this. Okay, so go ahead and hit pause. And when you're ready, when you've tried all three, I want you to hit play again. Okay, so we have the first two done. 3 squared is 3 times 3, which is 9. Number 2, x plus 3 quantities squared. We have to multiply a binomial times a binomial. There is also a pattern that you could use. I just multiplied x plus 3 times itself. You could think of that as foiling, distribution. There's lots of ways that we can do this. You could use a box. For example, you can make a grid that looks like this, x plus 3, and then an x plus 3, and then you multiply inward. There's multiple ways that you can multiply a binomial times a binomial. But we do need to combine like terms here. So we get 3 squared and 3 squared are like terms that can combine into 6x. And this is our final answer, x squared plus 6x plus 9. And in number 3, it's almost identical except we have a 4 all the way in front. So this part is going to become the x squared plus 6x plus 9 that we just got. And then what I'm going to do is another step where I distribute this 4. So 4 times x squared is 4x squared plus 4 times 6x, which is 24x, and 4 times 9, which is 36. All right, so if you remember from the last assignment, the last workbook assignment, we had some patterns. There were 3 patterns, 2 of which we went over in the last video. The first one was the blue, white, green tile pattern. The second one was the class president, where we had 3 people tell 2 people each day. Then those people told 2 people. And then the last one was a backyard patio design that looked like this. So what we want to do is describe the growth pattern for each scenario. Okay, I'm gonna just call them scenario A, B, and C. And we can get, we can look at them individually. So let's do A, for example. So we have a design number. We want to know, how are we going from the design number to, say, like the number of tiles? Okay, let's think about that. So to look at this a little further, let's make a quick little table over here of design number, which I'm going to call N, and total tiles. Okay, so this is just the design number. So for design number 1, 1 tile. For design number 2, it was a 3 by 3 square. So it's almost like 3 squared, which became 9. and then design 3, which was 1, 2, 3, 4, 5 by 5, which was 5 squared, which is 25. So if we look at it, we're squaring a number, obviously. Let's think about, how do you get from 2 to 3, the number that you're squaring? And then how do you get from 3 to 5? Okay, and we can also think in the first one, this is 1 squared, which is 1. So how do you get from 1 to 1? So we need a pattern to get to the number of the edge number, right? And we can see that we can take 2 times the design number. So like 1 times 2, 2 times 2, 3 times 2. If you double the design number, that gives you 1 more than the actual edge. So let's just subtract 1. Okay. Previously, I think I did 2 times n minus 1 plus 1, but that is actually fine. It's equivalent. It works, but it's a little bit more complicated, right? If you distribute the 2, you get 2n minus 2, and then if you add 1 to it, you get this again. So my expression in the last video was completely equivalent to this one, but this one's a lot simpler. Okay, so basically, if I have n tiles, does a design number, the number of tiles I have is 2n minus 1 squared. A lot simpler than what I was doing before, but they're both equivalent. It was working, it just was a little bit more complicated. So we can kind of basically describe the growth pattern as basically the total number of tiles is double the design number minus 1 squared. Okay, so let me go back down here to write this. The total tiles is the design number doubled or multiplied times 2 minus 1 then squared. I'm writing it in words, but we can also write it as an algebraic expression. Okay. Go ahead and look at the other 2 patterns and see if you can come up with a pattern for that, or a description of the growth pattern. So go ahead and pause. Pause time. All right, and then go ahead and try B and C on your own. And then when you're ready, you can unpause it. Okay, so for B, which was our election, we started with 3 people, and then they each told 2 people, so it doubled each day. So the number of new people who found out about the secret doubled each day, but it started at 3. For C, the total number of tiles was going to be the design number times the design number plus 2, and then plus another 2. So let me explain. The design number times the design number plus 2 was this rectangle in the middle. This is just one way to think of it. There's multiple ways to think of it. But if you look at this rectangle in the middle, its dimensions were the design number, which I'm calling n, so in this case 2, times the design number plus 2. So it's 4, right? That's 2 more than 2. We can verify it here as well. Okay, this is 3, which is the design number, and this is 5, which is 2 more than the design number. So you multiply those together, like in this one, you get 15, and then each time there was an entrance and an exit. Entrance, exit, entrance, exit. That was constant each time. So you just go ahead and add 2 more for the entrance and the exit. That's an and sign. Okay? All right, now we can describe how the quantities change relative to each other. And hopefully you can notice that things are increasing. Okay? With the design number increase, all of these are increasing. We could say that. So the number of tiles here is increasing with each. The number of people who know about the secret is increasing. The number of tiles in the first thing are increasing. So we could say that they are increasing. They are increasing. All right, let's look at them a little bit more in depth. Okay, so activity 1 is just focusing on the first pattern, the flooring. All right, so describe the number or the patterns of new tiles as that an employer must add to each design. Is the pattern linear, quadratic, and exponential? So let's put a pause on the book for a second here and let's identify what these terms mean. What is linear? What is quadratic? What is exponential? They were things that you learned in Algebra 1, but we need to review them. Okay, so I have this chart here. I recommend that you copy this down in your notes so that we are comparing each of these, okay? Linear functions have a degree of 1. What that means is their highest exponent is a 1. We don't usually see the 1, but you know y equals mx plus b, right? Y equals mx plus b, the x has an exponent of 1. That's why we say it's a first degree polynomial, actually. Now, we haven't gotten too much into polynomials yet, but, well, you've seen polynomials in algebra, so. What else do we know about linear functions? Linear functions have a constant rate of change. That's the slope. Constant rate of change is the slope, the m. In case you want to remember what the b stands for, it is the y-intercept. And a linear function has something called constant first differences. Now, in order to check to see if something has constant first differences, you have to look at the table, a table of values. Okay, so I'll come back to that in a bit. Okay, and you can think of it as we're adding the same amount each time. So if you remember arithmetic sequences, such as like 5, 8, 11, 14, we're adding 3 each time. That's an arithmetic sequence. That's pretty much what's happening to your y values. You're adding by the same amount each time. Okay, it might be a whole number, it might be a fraction, it might be negative and going down. So here's a graph. It's a line. Linear functions are lines. Okay, let's look at a table of values of this particular graph and see what do I mean by the first differences are constant. Okay, so I'm going to make a table of values for this graph. Hold on. Okay, so by the magic of technology, I have made this graph and its t-table match. Okay, so these are some of the points. Now, it's important when you're doing first differences that you notice that your x values are going in increasing order by 1. So we can see that it's increasing by 1 each time. So to find the first differences, what we're going to do is we're going to see how is the y changing. First differences. So how do we get from 1 to 1.5? So sometimes you could just look at it and go, okay, I added a half. It went up a half. If you're not sure, you can take one y value and subtract it from the previous value. So 1.5 minus 1 gives us the half that way too. Okay, I keep going down the list. 1.5 to 2, it increased by a half. 2 to 2.5, it increased by 1/2. 2.5 to 3, it increased by 1/2. See how they are the same number each time. These differences are constant, which means this is a linear function. All right, so now let's look at another type of function, quadratic. Okay, quadratic functions have a degree of 2, which means they have an x squared as its highest power. And you may remember this from algebra as well. It's usually the standard form for a quadratic is ax squared plus bx plus c. And its second differences are constant. So what is the second difference? Well, let's make a t-table for this guy. So this is what a quadratic looks like when it's graphed. It's essentially what you may remember as a parabola. All right, so I'm gonna go ahead and make a t-table for this, and we'll see why are the second differences constant. Okay, so here's our t-table for the graph, the parabola that you see there. It's just a basic function of x squared. It's just like the simplest parabola. Okay, the first differences need to be found before you can find the second differences. So the second differences are the differences of the first differences. So we're going to do the same thing we did for the linear function. We're going to find the first differences. So I'm going to write first diff. Okay, from 4 to 1, it went down by 3, so -3. From 1 to 0, it goes down by 1. So we can already see that these are not constant. This is not a line. From 0 to 1, we can see it went up 1. And from 1 to 4, we can see it increased by 3. Now we're going to do the second differences. So I'll put it just to the right. I'm going to take -3 to -1, and I'm going to ask what happened. To go from -3 to -1, it went up. It went up 2. To go from -1 to +1, it went up 2. And to go from 1 to 3, it went up 2. So we can see here, we're getting 2 each time for the second differences, which means the second differences are constant. And that means that this is a quadratic. All right, and the last type of function we're going to look at is exponential functions. Exponential functions, let's see which, have a variable in an exponent position. Okay, and they can look like this. Y equals a times b to the x power. They can also be a little bit shifted, like you might have a -h plus k, where that just means it got moved left, right, up, or down. But notice that the exponent is an x. That's the key part of an exponential equation. So exponential equations come about by multiplying by the same amount each time. And essentially they're related to geometric sequences. So geometric sequences is a sequence of numbers where numbers are being multiplied by some common thing each time, a common ratio. So maybe it starts with 5, and then it becomes 15, then it becomes 45. So you may notice that I am multiplying times 3 each time. And it would continue on in this pattern. 45 times 3, I believe that's 135, and then it gets big very quickly if we're multiplying by a whole number like that. Okay, exponential equations. This is an example of an exponential growth. There's also exponential decay, but for just this example, we'll do a growth. And what happens in the t-table? Well, their first differences and second differences don't really show up, but you can see that the y values are being multiplied in some way. Okay, so let me show you this one right here. All right, let me make my t-table and then we'll look at it. Okay, so here's a t-table of the points that we were just seeing in that graph. And if you try to do the first and second differences, it's not going to be helpful. But you have to recognize in this one that we're multiplying by a constant number each time. So we're going to think of it as a ratio. 1/2 to 1, you can multiply times 2. 1 to 2, we can say we can multiply times 2. 2 to 4, we're multiplying by 2. So the key thing here is it's multiplying. And we call this a constant ratio. Okay, so now we have hopefully a better idea of what's the difference between these three types of functions. All right, now let's go back to the question that we were being asked. Describe the pattern of new tiles that an employee must add to their design, and is the pattern linear, quadratic, or exponential? Okay, so this is not total tiles, this is add tiles. What are we needing to add? So let's make a table. If we got to be able to make a table to see these patterns. Right now there's no numbers, there's just this visual. We need the numbers. So let's go ahead and make a table. And our table is going to have the design number and the number of new tiles, okay? Actually, instead of a new table, let's just count how many new tiles there are and see if we can look at the pattern of just the new tiles. So from design 1 to design 2, we added the white ring, which is 1, 2, 3, 4, 5, 6, 7, 8. And then from design 2 to design 3, we added 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Okay, and if we had design 4, I'm just going to pretend I'm going to draw the tiles that would go around. There'll be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. So for the next one, we would add 24. Okay, so the pattern of the new tiles of 8, 16, and 24, we can see that that is going up by 8 each time. Anytime we have a pattern that is increasing by adding the same number each time, remember, that is linear. Okay, so our answer is linear. So the pattern is linear because it is increasing by 8, which is constant. We're adding 8 each time. Now we're going to write an expression to represent the number of new tiles that an employee must add to an n-square floor tile design to build the next design. Okay, so n represents the number of tiles along each edge. Okay, so I've used n to represent the design number. This n represents the number of tiles along each edge. So let's make sure we understand that difference. So n would be the number of tiles along each edge. Okay. Just 1 here, 3 here, 5 here. So we want to write the number of new tiles being added in terms of that number, the edge number, okay? So I'm going to write if you ever have to write an algebraic expression or an equation, write it out like as a sentence first and then turn it into math. So for example, I want the expression to represent the number of new tiles. So number of new tiles to add equals, well, now we don't know the rest of it yet, but we'll make a table. So let's say, so n, just the edge length, and new tiles. Okay, so for let's see here. So if we make a table with the edge number and the number of new tiles, you get the edge is 1, we have to add 8. When the edge is 3, we have to add 16. When the edge is 5, we have to add 24. Why? What's happening? So I want you to imagine this first design, the edge 1. Where did the 8 come from? Well, there needs to be one here, 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 and here. You have to fill in the sides, but then there's also like these 4 in the corners here to make the square, right? See how that works? So that was 1 for each of the sides, because the side length was just 1. Okay. And then we added those corners. So let's look at the edge length of 3. Well, we're going to need 3 here, 3 here, 3 here, 3 here. Okay, but then we have these 4 corners that we have to fill in. So notice there's 3 on each side because that's the side length. 3 times 4 gives us 12, but then we have to get the other 4 that we have to add in. Let me make it orange like I did before. Okay, and for this one, get rid of my green dots, which were essentially the same thing I'm about to draw. Let's see, that was 16. Okay, so we're going to have 5, because that's the edge, on each. So there's 5. There's 5 at the bottom. 5 on the left. 5 on the top. And then again, we have those 4 corners. So this is just one way to think of it. There might be other ways to think of it about why it's always doing this. Okay, so the number of new tiles to add is basically 4 times the edge number plus 4 for the corners, right? That was the corners. So now let's plug in our variables, okay? Edge number was n, so really we get the expression 4n plus 4, which is a linear expression, right? Y equals mx plus b. It's a degree 1. We see that it's going to give us a linear, as we predicted in number 1. Describe what values of n make sense for this problem situation. So n is the edge number. Look at the edge number. We have 1, 3, 5. The next one's going to be 7. So we're only using odd numbers, positive odd numbers. Okay, so analyze the expression Ramon wrote to represent this pattern and his explanation. So design 1, 2, 3, new tiles 0, 8, 16. So anytime in the book you see this thumbs down, it means this is incorrect. And we need to probably analyze why it's incorrect. Yes, explain why his expression is incorrect. So the expression 8 times n minus 1 represents Miriam's square floor pattern. Okay. I noticed that the number of new tiles increases by 8 in each new design. So why don't you pause and look at that and see if you can figure out what's wrong with it. So, and honestly, I thought of it this way at first too, and I had to catch myself. The reason that this is not correct is because he's using the design number. That's not what they were asking. This should not be the design number. It should be the edge number of tiles along the edge, okay? So something about the fact that he's using the design number when we were supposed to be using the edge number. Okay, so Miriam asks her employees to determine the number of new tiles added to Design 2 to create Design 3. Each employee describes a unique method to determine the number of additional tiles needed to create Design 3. Represent each of her employees' explanations with an algebraic expression that describes how many new tiles will be added. So basically, her employees came up with an expression in different ways. Let's identify what those different ways are, get the different expressions, and then we're going to show mathematically that they are actually equivalent to each other. Excuse me. Okay, so Wilma said I must add 3 tiles on each of the 4 sides. Okay. 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3. Then I must add a tile for each corner. So basically she did it the way that I thought of it, right? We're gonna do 4 times 3 plus 4 because the edge is 3 from the previous one. The previous edge was 3. So remember the previous one looks like this. And that's where these, right, this was the previous one. So we do 4 times n plus the 4 corners. So Wilma did it exactly the way that I thought of it, okay? Now we've got 3 more. We got Howard, Tyler, and Tamara. Okay? Go ahead and read through their description and try and come up with their expression, okay? So I want you to pause, read through each of their descriptions, and remember n is the number of tiles, right? In their example, n is 3, but you're going to replace it with n. Okay, and you're going to go through all 3. Okay, so pause it, take a few minutes, try all 3 of these, and then we'll go over it. Okay, so for Howard, he sees it as the top and the bottom has 2 extra tiles from the original edge. So the original edge was 3, but they added 2 on each end. So the 2 on each end were these 2. So we have 3 plus 2, and then there's 2 of them. There's a top and a bottom. And then on the sides, it's just the edge. The edge number was 3. So it's just 3 on each side, but there's 2 of them, which is why there's a 2 here. So in general, if the n is 3, that was the number of side on the edge. So I'm going to replace the 3's with n, and we get 2 times n plus 2 plus 2 to 2n. All right, what about Tyler? So Tyler did something similar to the way that I thought of it, which was the first one, Wilma. He said, I need to add 3 tiles 4 times and then add the 4 corner tiles. Okay, so the 3 tiles 4 times, there's 3, 3, 3. So he's going 3 plus 3 plus 3 plus 3. And then he's adding the corners, which is there's 4 blocks. So we can write it as n plus n plus n plus n plus 4. It technically works, it's just not the most efficient because we know we can combine like terms, but we'll get to that later. All right, and the last one, Tamara. So Tamara thought of it as 2 squares. There's an original square in the middle, which is a 3 by 3 square. Okay, so that's the 3 times 3. And then there's the large outside square, which is the 5 by 5, which would include that 3 by 3. And she's subtracting them. She's taking the whole thing, which was 5 by 5, and subtracting the original, which is 3 by 3. So let's think about where does that 5 times 5 come from? That's adding 2, okay? So that would be n plus 2. And instead of writing it times itself, I'm going to square it. That's this part. Then I'm going to subtract the inside, which is n times n, so or n squared. So now let's look at why they are equivalent to each other. I'll let you answer 6 on your own. Which expression do you think Miriam should use? It could be any of them, okay? I'm going to skip to number 8 because I want to talk about how each of them are essentially equivalent. So use each expression to determine in question 5 to calculate the number of tiles that an employee must add to squares with a side length of 135 to create the next design. Okay, so we're going to use 135. So let me write out each of their expressions. Okay, now we're going to let n equal 135. So in each of these expressions, I'm going to substitute 135, and then we're going to simplify them, okay? So let's see here. Do 4 times 135 plus 4. And then we're going to do 2 times 135 plus 2 plus 2 times 135. And then this is going to be 135 plus 135 plus 135 plus 135 plus 4. And then the last one's going to be 135 plus 2 squared minus 135 squared. Okay, so use the order of operations, use a calculator, simplify all of them, and see what you get. So go ahead and pause. Simplify all of these and see what you get. So what you should get is that they're all 544 tiles. What shows us that all of these methods, even though they're a little different, all are equivalent to each other. And we can use algebraic methods to show that they're equivalent to each other, such as distribution, squaring, combining like terms. Eventually, they'll all become the same thing. Okay? All right, so there's a few more questions in activity 1. We're going to just do number 10. I'm going to show you those algebraic expressions are algebraically equivalent without plugging in a specific number. So we're going to look at the different algebraic expressions. So let's take, for example, n plus n plus n plus n plus 4. Well, combine like terms, that's 4n plus 4, which is the same as Wilma's. Okay, let's take the other one, 2n plus 2 plus 2n. We can use the distributive property. Get 2n plus 4 plus 2n. Then you can combine like terms to get 4n plus 4. Same thing, it's getting Wilma's again. And then tomorrow's is the most complicated, but it was n plus 2 squared minus n squared. We're going to have to do a little foiling or multiplying binomials. So I'm going to expand that, and I'm going to do n times n is n squared, n times 2 is 2n, 2 times n is 2n, 2 times 2 is 4, minus n squared. And then you'll notice the n squareds completely cancel, and then I can combine like terms again, and I get 4n plus 4. So you can all they can all simplify down to what Wilma's was, 4n plus 4. All right, so there's a couple more patterns that you have to look at, okay? And so make sure that you use the answer key to help you, not copy it, but to help you on these ones, okay? And don't forget, if you're still struggling, please come to my office hours where I can help you individually. But that's going to be it for this video. Hopefully that will get you started and will help you through this lesson.